So my name is Guillermo. Thank you for coming out. Thank you for the invitation. Super excited to talk to you guys about LOCALIZATION and our experience. So we try to help people maintain healthier eating habits, and we do that by allowing them to keep the easiest food diary that you could keep, I guess. That's the intention. And the title of the talk is What I Learned from Looking at a Million Pictures of Food. And I didn't actually look at a million pictures of food, but clearly the intention is that our algorithms would look at a million pictures of food. And I'm going to try to describe why it was difficult and why you would even try to do something like that. So I guess the first thing that I learned is that people are crazy about bananas, and I didn't expect that to be true, as in I did not expect that snack to be so popular, particularly because it's sort of healthy. But then again, it's sort of packed with sugars, so maybe it's not that healthy. So maybe that's why. This I did not expect, though. I thought that was a trend, like the avocado on toast, but it remained constant, a very popular food item in our app. And you can see why. They look delicious, and I'm a convert now. This, though, was the most popular food item on our app. Black coffee, no milk, very simple, which I can relate to, but I didn't expect in the UK. I thought it would be tea in the UK. So you guys let me down in a way. This I totally can relate to because I can't start my morning without two of these. Anyways, give you a little bit of context. This whole thing started because it's very difficult to keep healthy nutrition, right? In reality, you can intuit why incentives, commercial incentives in particular, make a lot of foods that are packed with sugars and certain types of fats very available to you. And I was certainly that person. I felt 2.5 years ago, maybe 3 years ago, super uncomfortable with my weight, with how I felt after exercise, and that started the process. And I would do what any rational, analytical person does. I went to the University of Westminster and got a lot of tests done on myself. I wanted to know how I worked. And there was one test in particular, really two tests that are mixed. You sit down, you lie down on a table, and you pretend to sleep for 60 minutes with a gas mask over your face. And when you breathe, the machine measures the respiratory quotient, the amount of carbohydrate versus oxygen that is released. And from it, you can tell the resting metabolic rate, essentially how much energy you consume at rest, but also substrate utilization. Where does your energy come from? What do you metabolize? Carbohydrates, proteins, fats? And I thought that was super interesting. In particular, it told me that I couldn't outrun or out-gym or out-exercise my very poor nutrition. After I started reading a bit more about it, I did what hopefully most people do. I consulted an expert, and the nutritionist told me keep a food diary. So I did. And that's where LOCALIZATION started. A food diary nowadays feels anachronistic. Like it doesn't feel like it belongs in 2017. I had to enter things manually. Sometimes I didn't find it in the food database. My expectations certainly weren't met, and I thought that we could do better. So we tried to do better, and that was the genesis of LOCALIZATION. And so why do you keep a food diary? Why does a nutritionist tell you to start logging your foods for a week and then go over them with you so that you become aware of what you eat? And that sounds simple, but it is not at all. And you can see this problem of awareness, particularly awareness over time, repeated over and over again. Think about how many people you know that save for retirement when they're 20 or 22 or 25, or how many people stop smoking too late. And too late is very relative, but you should just stop smoking now, right? And it's the same in nutrition. It's very difficult for us to understand the effect of small actions as they compound over time. And yet, and I guess this is why we're all here, or at least most of you have some interest in AI or machine learning, as animals, we're incredibly adapted to perception. We perceive our environment incredibly well. So this discrepancy between perception and awareness over time is the thing that was the main motivator for us. Okay, now into the more technical bit. Hopefully there's a good balance between technical and non-technical, but you'll let me know. Teaching a machine to see, in particular to see food, for us meant for problems, classification, pretty typical, localization, where the thing is that I want to find, semantic transfer. Can I take some ideas that I know from a different domain or a different modality and apply them to my domain, and vocabulary extension. Your food is served. You have a plate of delicious pasta. You take your app out, and you're about to take a picture of it. So the first thing that we have to do is we have to recognize what is in that picture. Object classification. Is that a bicycle? And that really is a search for invariance. How do we find some method that allows us to recognize a banana once it's rotated, a banana when I open it, which means it's deformed, when I have half of it, which means it's occluded, right? I took half of the object that I'm trying to recognize, it no longer exists because it's in my belly. When it's small or large, or I change the angle of the picture. All of these different scenarios under which I have to be able to perform recognition is just the search for invariance, right? Can I find invariant features, or at least an invariant method? And that takes us to this. You probably have all heard of this, hopefully, maybe not, but it's relatively simple. It's not particularly, it's inspired by biology, right? It's not actually how neural networks work, not at all. But it's inspired by biology insofar as there are a number of inputs that sort of represent what dendrites would feed into a neuron, and then an output axon, which is the output of the function that's computed over those inputs. In a very simple way, it's a function that computes over each input times a weight that you learn over time, plus a bias. Very simple. You produce that output, and then you put all these neurons together. At the beginning, we put them together in a highly connected way. They were called MLPs, multi-layer perceptrons, and they were all very highly connected. And in fact, there's some interesting math that shows you that this is a universal function approximator, but it's very expensive. To move a bit into the future, you start thinking about these deeper networks, particular convolutional neural networks. That's what we used. And you can think of the depth as different layers of abstraction. Right? So the first layer, when you're learning through this network, ends up recognizing filters that used to be hand-coded, things like Gabor filters. So if you were a computer scientist in the 1980s or 90s, you would have, if you were in computer vision, you would have come up with little kernels, which are like little matrices, that would go over a patch of image, and the matrix would produce a result that you believed was an important thing, like an edge detection or some sort of gradient detection. And you don't have to manually code them now. You can sort of learn those features. Importantly, though, at different points in the depth of the network, the neurons in the layer represent different degrees of granularity, or rather abstraction, right? So take lines or Gabor filters, mix them together, and you have textures or complex edges, and take one step above in abstraction, and you have concepts. We'll go into this into a lot more detail, which hopefully you'll be okay with, or it'll be interesting to you. Anyways, so the next step was object localization. Where is the bicycle? That was really difficult for us because food is, in particular, difficult to do object localization with because it's usually mixed, right? So you have a salad, and the salad has avocado and has mushrooms inside of it and has green beans and all this lovely, delicious food, but it's mixed and some of it's hidden. Or you can have things like rice, pearl barley, pilau rice, quinoa. Right? Slightly different, but very different from a nutritional profile perspective. And this took us a long time, and I spent more time than I should have trying to solve this problem. We arrived at a solution that we called foveated object candidates. And all that really means is if you take a network that you use to learn food, or a reduced number of classes in food, and then chop the network's head off, and then take the top and turn it into either a binary classifier or even a reduced set of classes, then when you retrain that network and then chop its head off again, you can deconvolve. You can take the last set of features and project them outward into the image again, which will give you a map. Essentially, it'll take, depending on your strides, a shape or a color of where there was food or the reduced number of classes. Once you have that map, so in this case, clearly there was an olive here. Once you have that map, then you are able to restrict the number of object candidates, the things that could be different objects, in a very significant way. And more importantly, you foveate the candidates. So you take the center where the interest point was that the map gave you, that original network gave you, and you only concentrate the object candidate there. What do I mean by only concentrate? I actually mean blur outward. Like the resolution remains the same for the center, but outside of that, you lose resolution. Why would you do that? Because there are places where you have 2 or 3 peas, or like a plum tomato, or things, and this might be very specific to food, but anyways, we found it super useful, but took us a long time to get there. The next step was semantic transfer and vocabulary extension. And these two things are sort of related, but the one that matters the most is semantic transfer. If I show you the food on the right, it's like a pressed salad. Most of you probably know it. And if I ask you what the foam on the left is, what do you think it is? What is any guess?
Cream?
Foam on the left?
Cream cheese?
No, not the cheese, but the foam right on the left, right here.
Matcha.
It's basil or matcha, basil. Who said basil? Basil? Why did you think it was basil?
Because she's an expert.
It's because it's the equivalent Super Master Chef fancy version of the other thing.
That's exactly right.
It's a fancy version.
That's exactly right. So what you just did, you took a bit of knowledge that you had about compressed salads, right? And that knowledge is a semantic representation, right? It's some representation of the meaning of things, and then you applied it to a different modality, to images. And there's a ton of research around how you take image data and then other types of data, say text data or other types of description data, and you train or you learn a joint embedding, so a space where they both live, such that points that represent something in text also represent the same thing in visual data. That's extremely useful because that means that you don't actually have to know all the foods visually. You can know them in a different modality. Key thing, the next thing is very simple, vocabulary extension. When you're thinking of building your models, make sure that you think of building them in such a way that when you add classes, the cost of adding a class, as much as you can, becomes logarithmic, not linear. So if every time that you add a new class, if I want to learn a new food, I have to add 100,000 images, then that's an intractable problem, right? Okay, so if we as humans are so good at recognizing food, right? If you, when you look at a piece of pizza, immediately say pizza without any cognitive effort, why would you even try to do it through a phone? And it wasn't just like an intellectual vacation. It matters. That number is crazy to me. In 2016, the National Obesity Forum did a study and found that 2/3 of people in the UK are either overweight or obese. And that has, in the UK. In the US, it's higher. In the US, it's
It's just British people, not immigrants.
oh no, I'll let you answer that question. So, regardless of the origin of the people, it's particularly relevant, that question, I suppose, right now. Regardless of the origin of the people, it has a significant consequence on our services, on the NHS, but most importantly, on those people, right? Most of those people have a form of metabolic derangement. And metabolic derangement over time has serious health consequences. Like it's the highest linked all-cause mortality factor, right? This is going to affect your life. So that number was big, but we decided to do some extra study, I guess, to question a bit more. We ran a number of surveys, and the average numbers for those surveys ended up being at any point in time when we surveyed, 80% of people had tried a diet in the last 12 months, 33% of people were on a diet. These were in the UK and mobile users, so there is some bias. We thought that was incredible. So it led us to this. This was what we wanted to do. This was the goal. The goal was to take people from focusing on now, I had a tough day Thursday, I don't have any time, I'm going to go eat some junk food, to focusing on both now and the future, right? Realizing that the consequences of your actions, but not in an onerous way, not like, oh, I feel terrible, but rather you become accustomed. And also from, I need advice, tell me what to do, to I'm self-sufficient. Essentially to a point where we were redundant, right? Nobody really needed our app if it worked, which you should never tell a VC, because it's not a very good It's not a very good commercial model. Give me more. Okay, so here I'm assuming that a lot of you are very technical people, so you actually want something that you can use. And I hope that is the case, because what comes up now is more technical. So the best way for you to learn, I suppose, from anything that we've done, is to tell you all the mistakes that we made. So that's what we're going to do in 2 ways. First, technical. So the first point, data processing matters a lot. No, read it again. It matters. Like if I stop the presentation now and that's the only thing that you learned, it would be that one. The amount of time that I spent correcting mistakes in separation of training or validation of test sets, or in archiving results from a model or a set of experiments on models relative to the way that I'd cross-validated or separated data sets is ridiculous. I spent too much time doing that. Absolutely no value in that time. Next step, and this is now specific to convolutional neural networks and images. So this isn't true for recurrent neural networks or LSTMs or anything like that. Do not decorrelate or whiten your data. As in, like, some people think that it works, but it's so much effort to do it properly. So we tried first doing it over the entire data set, PCA. So decorrelate, separate the principal components so that they were orthogonal, and then use those in your filters. But images are highly dimensional, right? And a large data set of images, forget about it. So there's alternates. You can take a window, like a little kernel that passes over your image as a patch, and then from that you whiten, right? Or you do PCA. Even that we didn't find was extremely useful. It took us a long time to find a way to take a large data set and do that, and the results were underwhelming. Only mean center your data. Only take the mean image and take that mean image out of your training data set. If you want to be a bit fancier, and I think it works better, mean center each channel. So red, green, and blue. Do not do this for your validation or test sets, only for the training set. Okay, weight initialization mattered. Okay, mattered for some reason, but weight initialization matters. So imagine that you take your neural network and you initialize all of your weights to 0. Does anyone know why that would be a bad idea? Yeah, some people know why that would be a bad idea. Exactly, you would learn nothing, right? So if you put your all weights to 0, then you remember that function that took all the weights, all the inputs times the weight plus the bias? Then if you do that, the gradient relative to each input ends up being the same, which means you don't transfer anything of use backward. There is symmetry, and the symmetry is useless. So if you break symmetry, you could do something like that. You could say, okay, I'm going to initialize my weights as a small number times some sample of unit Gaussian. Right? That could work, right? Let's say you have a tan h as your activation function. You do that. But as soon as you start building a deeper model, what actually happens is all of your activations, at this stage, you're really just initializing, right? All of your activations collapse down to a very tight, very narrow distribution around 0, which is completely useless. Because if you think about the local gradient of a neuron relative to its input, it's proportional to its input, right? So if you get a very tiny number at the moment of activation, then the gradient will be tiny as well. And that is a problem, particularly for deep networks, right? For shallow networks, it ends up not being that much of a problem. So just use Xavier initialization at the beginning. Of course, if you think about Xavier initialization, what it does, you naturally should have a question about rectified linear units. What happens with a rectified linear unit if I'm doing regular Xavier? And I don't know if anybody intuits what would happen, but like a rectified linear unit is a hinge function, and that means that anything below 0 ends up being 0, exactly. And if everything is 0, then your gradient 0, so everything gets killed, so you half all of your potential learning. Very simple to fix. Most modern libraries fix it now for you. You just have to add a factor of 2 at the calculation of the denominator, and that's why I put matters ed. Because nowadays you can just download TensorFlow or MXNet and it'll do a lot of this for you. All of this, forget about all of this. All of this is just about ensuring that most of the neurons in your network are active. And that's the main thing that I would want you to get out of this slide. If you train a neural network, after you train it, take your training set or sample your training set and run it through the neural network again and sample the neurons. And when you sample the neurons, at least the activation statistics, you'll see how many neurons are dead. How many neurons did nothing? And if the proportion of neurons that are dead is very high, then you're in trouble. Okay, I'll go super fast because there's still a lot more to cover. Fat networks suck. Sorry, go ahead.
I went to Google Next and they talked about recursive neural networks.
Yeah.
Or something. I don't know, but that should do it for you, right? Where they retrain.
Well, slightly different. So a recursive neural network won't use the same type of activation function, still has the initialization problems, but it's a different, I guess it's a different structure, although I'll touch on something similar soon. Okay, so you have these, what do I mean by fat networks? The 2012 paper, AlexNet, is suggested, super interesting, though very highly connected, right? A lot of fully connected layers, that means a ton of parameters. They were great, but they're not super great now, so don't use them. Or maybe use them to learn, but I would use them right now. Large strides and large pooling layers have some problems. In particular, large strides, that means the kernel that you move across the image when you're thinking about this input. Miss granularity, though they are useful when you have low GPU memory, so that might work as a first layer. And then large pooling layers lose a ton of information. Think about what a pooling layer is. A pooling layer is taking a ton of information and then either averaging it or choosing a max. The larger the pooling layer, the more that you condense the information and thus lose detail. In our context, smaller networks work better because we try to fit the network inside our phones. Okay, in the end, batch normalization and residual networks are manna from heaven because batch normalization actively, aggressively says, I hate the problem of initialization and I'm going to try to solve it by purposefully normalizing. But the normalization function is differentiable, which means you can learn it through backpropagation, which is incredible. That's fantastic. Those people are super smart. And then residual networks, that's also super incredible. Read that deep residual learning for image recognition paper. Super interesting, but the intuition is very simple. The function, instead of being f of x, ends up being h of x, which is f of x plus x. And if you intuit what that means, if f of x didn't add anything and backpropagation works, then backpropagation ignores f of x and just takes x, which means batch normalization allows you to say, for things that don't work, just use identity mapping, which is really useful. Finally, if you read that paper, there's a subsequent version of that paper that describes shifting. This is our batch normalization unit, but you might find different units might work for you. Shift the order, that order might help.
Just a quick question. Do you find that mean centering your data is still important if you're doing batch normalization?
No, it's not that important actually, because batch normalization takes care of centering. Yeah. Okay, so if I take all that and just say starting out, what do you do starting out? Very simple. Default to a simple model first. Don't try anything fancy. After that, default to, if you have an activation function, use rectified linear units. Don't use anything else. In fact, if you can, use some rectified linear unit that does not saturate. So a soft ReLU or a leaky ReLU or a dynamic ReLU. And then if you have few samples, don't think that these methods aren't for you. You can take a network that's already trained, chop the head off, find the part that you think you should retrain, and then retrain by running examples again. And then if you're initializing, use Xavier initialization. Okay, next steps. A bit more advanced. If your data set is about 1 million unique images, go straight for ResNets, shallow ResNets. Don't do any transfer learning. You have enough data to actually get more mileage from training raw. After that, use don't separate your methods for object proposals and classification. Train them together end to end, either with a single loss function, is a bit more difficult, or 2 loss functions. And then, that's a copy. Okay, how are we? We're 3 mistakes, 3 minutes. Okay, this is much more important than everything else that I told you. Tech does not matter, in particular when it works. When technology does not work, you forget it's there, you form a habit, it's doing its job. That means that the arc of the experience that your product provides is crucial. Think about how your product brings people back, how it makes them feel. That is the most important thing that you could be thinking about right now. The cost of a poor experience is incredibly high, in particular in the context of applied AI. And I'm going to show you an example. The presentation of results really matters. The cost of a false positive is high, and the presentation sets up expectations. We did this at the beginning. It was a mistake. We thought that we were so good at recognizing that we would show you this big hero panel that told you what was in the food, but we didn't always get it right? And when you get it wrong, it's way more expensive than when you get it right. We provided 5 panels so you could scrape through, and we could do it infinitely, but imagine how poor an experience it would. No. Oh, okay, yes, that would be terrible, right? So we couldn't do that. We just provided 5 examples. So when we didn't get in that case, man, that was horrible. Much more importantly, this says that I will recognize every element in your plate. So even if I recognize every element in your plate, your expectation is now that the next item, the next screen, the next part of the app is going to be incredibly accurate. And you don't want to set those expectations, because in reality, nutrition information isn't incredibly accurate. And final bit of, I guess, mistakes that we made. Once all the tech works to a degree that you feel is commercially viable, then you open the real set of problems, what I find most interesting in trying to do these kinds of things. What is that real set of problems? Are you solving a real need? Will people pay for it? Does that mean that you have sustainable business? That's the meat of your problem. Ask users questions, meet them early, and when they answer your questions, ask them questions again and again until they don't want to talk to you because they feel threatened by you. Because really, that's the only way to validate. Validate with money early, that's debatable, but I think it's the first thing that matters. It's debatable because a ton of people think that money implies a friction that you don't have early on, but I think if somebody's willing to give you money, then it probably means something. And finally, speed is king. So in our case, it was better that the model was fast enough than it was a percentage more accurate, and we needed to have a strategy for dealing with missing items. In the context of data science, you will find missing values, missing items, or unclassed, or like missing vocabulary all the time. Be sure that you can deal with it. All right, I'd be remiss to not say we were acquired recently. I'm now working for a company called IntentHQ. IntentHQ does a lot of analysis, and we're looking for people who like to do analysis. So we're hiring for data science and development roles. Thank you for your attention, and come talk to me if you're interested in this kind of thing.